In this final section, we'll discuss galvanic corrosion and voltage series. When two different metals are immersed in an electrolyte, such as salt water, galvanic corrosion can occur. An electrolyte is typically a liquid, for example, salt water, that allows ions and electrons to move between a cathode and an anode. You can see two examples here where we have a zinc metal, copper metal in an electrolyte solution, and a second metal, in both cases iron. In the case of the zinc, the electrons are lost, so oxidized, and as that oxidation occurs, the zinc is consumed. In the example of the copper and the iron, the copper is gaining electrons or reduced while the iron is oxidized, and you can see that the iron is being consumed. The cathode is the metal that accepts electrons, or the reduction part of the redox reaction in the electrochemical reaction. So in this case, you see how the electrons are going from the zinc to the iron, or here from the iron to the zinc. The one that is accepting the electrons, the iron in this case, the copper in this case, is the cathode. The anode is the metal that donates the electrons, or the oxidation part of the reaction. So on the left, that would be the zinc. On the right, it would be the iron. The more active metal acts as an anode and will corrode faster than the less active metal, the cathode. The cathode is the metal that is being protected. The voltage series indicates the reactivity of different metals, so the correct anode can be found for the protected metal. So just based on that, we can see in this case that in the case of the comparison of these two metals, the zinc is more active and is therefore protecting the iron. In the case of these two metals, the iron is more active and is therefore protecting the copper. In the image on the left, zinc is more active than iron. So zinc is the anode and iron is the cathode. Iron is more active than copper. So the diagram on the right shows iron as the anode and copper as the cathode. By donating electrons, the anode atoms become ions and dissolve in the electrolyte. You can see on the left is zinc ions, and on the right, you can see iron ions. The flow of electrons to the cathode reduce the probability of the destructive anodic reaction. In other words, the cathode is protected. So the flow of electrons towards this iron cathode protects it. The flow of electrons in this case to the copper cathode protects it. Because the anode metal dissolves, you see how the anode is being consumed? It's decreasing here. It is known as the sacrificial anode. Voltage series, also called galvanic or electric potential series, is used to find the reactivity of metals, so it can be determined which is the anode and which is the cathode in electrochemical reactions. Nobility is also used for this purpose. The more reactive a metal, the less noble it is. When two metals are physically connected in the presence of an electrolyte, the least noble metal will be the anode and experience galvanic corrosion. In addition to nobility, the type of electrolyte and the surface areas of the metals contribute to the reaction. The more active substances, or the least noble, which you can see on the graph is towards the right, have a lower electric potential or voltage, or more negative. See the voltage across the top becoming more and more negative. They're at the right and top of this voltage series chart. So top right. The less active or most noble are to the left, and these tend to act as our cathodes. The greater the difference in electric potentials between two metals, the greater the corrosion rate of the anode. If I pick a metal from the bottom left, like graphite, and the top right, like magnesium, the anode, the magnesium, will corrode very, very quickly, versus if I chose two metals that were closer together, like magnesium and zinc. Example 1, voltage series. Two metals, zinc and copper, are placed in contact with each other and are submersed in a saltwater solution. Identify the anode and the cathode in this galvanic corrosion reaction. The answer on the next slide we will review, but let's just see if we can't identify these two metals from the diagram and see if we can't decide based on that. So zinc and copper. So here's copper, and zinc is at the top. Here's zinc, okay? So the one that is further to the right is more anodic. The one that is further to the left is cathodic. So in this case, the zinc will be the anode and the copper will be the cathode. Zinc has a greater activity or lower nobility. It is more reactive due to its lower electric potential. When we identified it here, you see its electric potential in this -1 range. So it acts as the anode. Copper is in this -0.2 to -0.4 range, is the cathode. The zinc will corrode, the copper will not. Example 2 for voltage series. Two metals, zinc and copper, are placed in contact with each other and are submersed in a saltwater solution. Which of the metals will react and donate electrons? We've discussed and identified these metals before, but let me just recircle them. Here's zinc, here's copper. Zinc is our anode. Copper is our cathode. I think I circled the wrong one. Copper is our cathode. So here's what we have to remember. At the anode is where oxidation occurs. Okay, and oxidation is a loss of electrons, right? And so that is the metal that will lose its electrons or react, in this case, to donate its electrons. So based on what we did in the previous example, determining which would be the anode, which would be the cathode, once we know that here, we can say that zinc will be the metal that reacts to donate its electrons. From the chart, reading in the middle of the data bar, zinc's electric potential in the middle here would be minus 1.03 volts. Copper here is minus 0.36 volts. The metal with the more negative potential will donate electrons. So in this case, that will be zinc. Here's example 3 using this voltage series. A nickel-silver bar needs to be protected from corrosion. Which of the following choices for a sacrificial anode will result in a greater corrosion rate of the anode? Copper or cadmium? So we first need to find all of these metals. So right here is nickel, silver. Okay, and then let's also find copper and cadmium. Okay, so both copper and cadmium have a more negative potential than the nickel-silver bar, so that's good. They will both act as sacrificial anodes, but the greater the difference in electrochemical potential, the faster that rate will occur. And so if we look here, the nickel silver is about 0.3, and the copper is about somewhere between 0.4, 0.5, whereas the cadmium is about 0.7. So the difference between the cadmium and the nickel silver bar is the greatest, and so the cadmium will corrode at a faster rate. I've extrapolated some data from the chart that we just estimated on the previous slide, just so we can see this even more clearly. The electric potential of the nickel silver bar is minus 0.28 volts, as read from the middle of the bar. The copper is minus 0.36, and the cadmium is minus 0.69 volts. Now we can find the electric potential difference for each combination of metals. For the nickel, silver, and the copper, we get 0.08 volts. For the nickel, silver, and the cadmium, we get 0.41 volts. So the larger difference is between the nickel, silver, and the cadmium. The difference in electric potential is greater for the nickel, silver, and cadmium reaction, so that will have the greater corrosion rate.